let's try to quantify our notion of real behavior now using what we call the van der Waals equation. Let's try to improve upon the ideal gas equation in terms of being able to describe the behavior of our gas. Okay, the van der Waals equation basically takes into account repulsions and attractions among the molecules, so you get a better explanation of the behavior, the real behavior of a gas. So things to consider are the fact that molecules do occupy a finite volume due to intermolecular repulsions. You can only get those molecules so close before they start to strongly repel each other. Okay, so when they're as close as possible, then they start to strongly repel. So we say there's a finite volume around the nucleus, the nuclei of your molecule, so you can think of that as a finite. You can consider your molecule as having a finite size. Okay, so because the molecules, so if I have this molecule right here, and I've got these other molecules here. Okay, this volume occupied by this molecule right here is not available for the other molecules to travel around in, right? So we say that the effective volume in your container that the molecules can roam around here is reduced by the volumes occupied by the molecules themselves. Okay? So the volume available for molecules to move about is reduced. And so if the volume available for molecules to move about is significantly reduced, okay, then the molecules will collide more frequently with the walls. And what does more frequent collision with the walls mean? Higher pressure. Okay? So you would expect your pressure to be higher than ideal. Okay? So if your ideal gas law says PV equals nRT, now V sub m here is V over N. Okay? That's your molar volume. That's another way of writing the ideal gas law. Okay, so we can solve for the pressure. According to the ideal gas law, pressure is RT over V sub m. Okay, but because of excluded volume, okay, because of the volume that's not available to the molecules, you introduce a correction term here. Instead of RT over V sub m, you write RT over V sub m minus B. So we introduce this correction factor, and that's called your excluded volume, and that is due to the size of the molecules. Okay, and you can, if you were to think of your molecules as hard spheres, then that would actually give you an estimate of the volume of the molecule. It's 4 times the molecular volume. Okay, the actual volume of the molecules themselves, not the volume of the gas, but the molecules themselves. Okay, now why does this correction not matter if you're dealing with cases where ideal behavior is observed? Well, at very low pressures, remember you say the molecules are very far apart, so the volumes occupied by those molecules are negligible compared to the total volume of the gas, the total volume of the container. But once you get them close enough, then these excluded volumes become a significant correction. It becomes a significant factor in terms of pressure. So there'll be more frequent collisions with the wall. Okay, and so if you subtract a number down here from the molar volume, what happens? You're dividing by a smaller number, right? So when your denominator gets smaller, what do you expect? The whole thing, the whole expression here becomes larger. So that would lead to a higher pressure compared to the ideal pressure. Okay? So your pressure would be higher than ideal. Now, what does it mean when the pressure is higher than ideal in terms of Z? So if the only thing that's happening here, let's say your molecules are not attracting each other. Okay? Let's just ignore attractions for now. Let's just say the only correction we're going to look at is repulsions. Well, if that's the case, then you say the pressure would be larger than ideal. Well, if pressure is larger than ideal, you can say that Z is going to be greater than 1. Why? Well, remember repulsion we said will lead to a larger volume than ideal if under the same conditions. You can also say, another way of looking at Z is this. For the same volume, okay, for the same volume at the same temperature, the ratio of the actual pressure to what the ideal pressure would be is also equal to Z. So not only is Z equal to V over V ideal, that's also equal to P over P ideal. Okay? And here's how you can show that. It's a mosquito. Okay, so pressure over nRT over V, right? That's another way of writing PV over nRT. I'm dividing both numerator and denominator by volume. Okay? So I have pressure over nRT over V. This, for the same volume and temperature, this is what the pressure would be, right? You compare that to the actual pressure, P over P ideal, that's your Z. So Z greater than 1 also means that your gas pressure is higher than what it would be if it were behaving ideally at that temperature in that container. All right, so Z is greater than 1, which is still consistent with what we talked about earlier when we said if volume is larger than ideal at the same pressure and temperature, Z is greater than 1. It has to do with repulsive forces. Z greater than 1 accounts for is due to repulsive forces. Okay? So we've got a slightly better equation here than the ideal gas equation because this one can account for repulsions. But we need to be able to account for attractive forces as well, right? So let's take a look at how we account for attractive forces. In addition to excluded volume correction, like I said, you need to account for attractive forces. So what do we have so far? What we have so far accounts only for repulsions. This is what's known as the hard sphere model, okay? So P is RT over Vm minus B. We said this is going to be larger than the ideal pressure, right? Now, pressure, if you recall, is due to collisions of your molecules with the wall, okay? So the more frequently they collide with the wall, okay, then the higher the pressure. The faster they're moving when they're colliding with the wall, the more energetic they are, the more force they exert on the wall, the higher the pressure, right? Now, what happens due to attractive forces? Let's imagine you have a molecule approaching a wall, okay? So this molecule is approaching the wall at, let's say, 400 meters per second. But you've got these other molecules over here that are attracted to that molecule, okay? So what will these other molecules do as this one molecule we're looking at approaches the wall? Will it slow it down, speed it up? Attractive forces. So it's going to pull back on that, right? So a molecule that would, under ideal conditions, a molecule would be approaching your wall at constant speed, right? But because of attractions from the other molecules in your sample, it's going to slow down a little bit as it approaches the wall. As it moves away from the other molecules, it's going to be pulled back by the other molecules, which are attracting it. So that would lead to lower pressure on the wall. Okay? So your effective pressure would be less because the attractive forces are going to pull back on those molecules that are approaching the wall. So in addition to this correction right here, we have to subtract, okay, from this expression something that would lower, you subtract something here so you can lower the effective pressure. So now, the reduction in the pressure, we say, is directly proportional to the square of 1 over molar volume. What do we mean by 1 over molar volume? What's molar volume, would you say? Number of moles over, moles over volume over moles, right? So what's 1 over molar volume? It's number of moles over volume, right? So that's really concentration, moles per liter. So the reduction depends on the concentration, moles per liter, N over V. Not just on the molar concentration, but the square of the molar concentration. Because it depends on how many molecules within that volume, how many molecules are affected. They're all affected, right? So the more molecules you have, more molecules are affected. But it also depends on how many molecules are affecting the affected molecules. So that's why you have a squared term right there. So this is really, we say that the correction factor here, the correction term, is directly proportional to the square of the concentration of molecules. The more concentrated your molecules are, okay, the bigger the correction you have to introduce because of attractive forces. The more your molecules will tend to be slowed down as they approach the wall. And so that lowers the effective pressure. So this equation right here is called your van der Waals equation. Okay? So what's the effect of attractive forces on Z? It tends to make your Z less than 1, right? So you have a battle here between repulsion and repulsive forces and attractive forces. Whether Z ends up being greater than 1 or less than 1 depends on which type of force predominates, attractive force or repulsive force.